Hello everyone. Today I will talk about well-known discrete distributions. Here you can see the list of famous ones, but you should know about binomial and Poisson distribution in details for your exams. The others I will go through them briefly just to introduce you to them because they are famous anyways, and in the future you may want to use them. And it's not bad to know about them in order to also appreciate binomial and Poisson distributions, which are very useful. So the simplest version we could name in discrete distributions is named discrete uniform distribution. In this distribution, all the points have the same probability. Like for example, if you throw a die, then to receive 1, the probability is 1/6. And we could say the same about, for example, receiving 3. It will be again 1/6. And you can define them in intervals as integer numbers. Like for example, A is the lower bound and B is the upper bound. And for throwing a die, A can be 1 and B can be considered as 6. So the interval that we are talking about is the closed interval from 1 to 6. But we know that only for integers we can have probability, right? So for example, what's the probability of 1.5 for throwing a die? Of course, this is 0 because we don't have a probability there. So 1, 2, 3, 4, 5, 6, and each one of these integers can have probability, which is 1/6. But how to find the probability for each one of them? So obviously, each one of the event over the total number of possibilities. And here we call them lowercase n. So how to calculate it? Here, 1 corresponds to the lower boundary and 6 to the upper one. So 6 minus 1 plus 1, which will give you 6. So this is the total number of possibilities or outcomes, as you know, that we talked about before. So for each one of these points, 1/n, as you can see in the formula. So 1/6. Now for other problems, not just throwing a die, if you change the value of A and B, you can receive different distribution as an uniform distribution. Okay, so we can call A and B here parameters of this distribution, because by changing their values you can receive a total different distribution. Okay, so whenever you hear me talk about parameters, it's related to that. And in our next lectures also we will talk about parameters and statistics and the differences between them. So that's another story which we will cover later in our future lectures. But for the time being, you should know that when we talk about parameters, we are talking about these variables which are very important in order to define our distribution. So for our uniform distribution, in case of discrete uniform distribution, A and B can be given, and based on that you can calculate the probability for each point. And this one is the cumulative version. Do you remember about this one? It means that when you want to calculate the probability here, everything is in the format of x less than or equal something. Okay, so this is the cumulative version, and that's the reason we have 1 here after it is outside the boundary, and this is more than value of 6, for example, in this example, as you can see. So if it is 7, then in the format of cumulative, so obviously all the values that you can get for throwing a die should be less than 7 anyway. So this is 100%. And I will also show you in one picture to even observe it better. So you can see here in this graph that we are again talking about throwing a die here, where we can correspond to this one. So each one of them has the probability of 1 over 6. And you can show them on the graph like this. So as you can see, between all of them, we have gaps, and there is no probability here. And if there is, we should say this is 0, right? Because whenever it's impossible, the probability, if you consider everything in terms of probability, should give you values between 0 and 1. So in these cases, it is 0, we just don't show them. Okay, and for finding the expected value and variance, also you remember we call them mean. Mean of the distribution, variance of the distribution. And this is the variable that we are talking about. So X has discrete uniform distribution. What is X? It's throwing a die, for example, in this scenario. So in order to find it, you can easily use the formula. You remember in the previous lecture, in order to find Ex and variance of X, we needed to do some calculations. We had the table corresponding to all the information we have about the distribution. Everything was constructed for us, but it was hard to find expected value, or even not hard, it got our time, you know. But in this case, you can use the formula and very fast find the expected value and variance. So this is good. And that's the reason we name such distributions, and we have the famous ones that we are talking about today. So it makes our job much easier when you know how to deal with each distribution. Now, if you understand that X follows a specific distribution, like in this case, discrete uniform distribution, it's very easy now to find the expected value and variance. So what you need to have, A and B, your parameters, and based on them, you can calculate N in order to find what is the variance. You see, you already need A and B, and by using this formula, you can find what's the value of N. For the example related to throwing a die, we already talked about it, and we know why this is 6 for N. A and B should be given to us as the parameters of population, and in the future, I will show you how we can estimate the parameters using statistics. So expected value of X. Now that you have the formula and you have values of A and B, as you can see, it is very easy to calculate this one. Or it was another option to, since we have all the values, like the way we did it for the tables that I showed you in the previous lecture, it's also possible to calculate Ex like this. But as you can see, this version is easier. Now assume that the problem gets complicated, not as easy as throwing a die. So this one can be helpful. And for the variance, it's good enough to find N, and you can find your final answer. By the way, when we use this notation, it means that approximately. And when you want to approximate your answers, your final answer, it should be in 2 decimal points. Okay, guys? And also I will talk about it later, that how we can approximate it, because sometimes I see that you, in the middle of calculations, you calculate everything in terms of 2 decimal points, and the value that you will find here will have error. So one time for sure I should talk about how to apply the calculations with no error. And in case of discrete uniform distribution, not necessarily related to the example for throwing a die, you can see that the graph should be something like this. And it starts always from 0 and goes to 1. So that starting from a point, you know that from this point forward, it will be always 1. In terms of throwing a die, it should be from 6. Okay, so here, as you can see, starting from 5, it happened, which is different from the throwing a die scenario. All right, let's go through another distribution. And before that, we should know about Bernoulli trials. What do we mean by that? A random variable with two possible values, 0 and 1. So we have only two possibilities, 0 or 1. And you can also call them success and failure. These terms, success and failure, we use them a lot also in binomial distribution. So I will show you what we mean by that. Like, for example, if you throw a die and say, what's the probability to receive 1? Then 1 here is your success. If you don't receive 1, like you receive 2, you receive 3, then that's your failure. It depends how you define success and failure based on what you are looking for. And sometimes this could be a negative thing. For example, you say to have a thalassemic patient, this is a success when you're finding the probability. So we should be careful how we define our problem. Now, Bernoulli distribution. So you already know about Bernoulli trials, so based on that, it's easy to understand about Bernoulli distribution. So whenever you receive the target that you are looking for, we call it success, and it has a specific probability. Like say, to receive 1 for throwing a die. So P should be 1/6. And what is Q? Q is the probability of failure, which is 5/6 in that example. Now, the good thing about Bernoulli distribution is that, again, you can find expected value of that and variance very easily. So expected value is the probability of success, and variance is the probability of success multiply probability of failure, and it's very easy to find. If you are interested to know how we show them that this is the case, please read the books. Otherwise, proving theorems won't be interested for computer engineers in general, but in any case, if you are interested, please check the book, and if you have any questions about them, if you don't get how it happened, then please let me know, so we will go through them for sure. And the good thing about Bernoulli trials is that they are independent, okay? So when you want to find the probability of outcomes inside these Bernoulli trials, it's very easy because by multiplying them, you can find. This equation holds only if all of them are independent, right? So otherwise, we cannot use this formula for all the distributions. Before introducing you binomial distribution, you should know about combination because we will use them in the formula. I have a video related to that about combination and permutation. What are the differences? I even solved some exercises related to them in discrete mathematics. So if you are interested, you can check it out on my YouTube channel. But briefly, I'm just telling you what's the difference. For permutation, order matters, but for combination, it doesn't matter. And that's the main difference between these two. You should know about counting. Again, I talked about it in discrete mathematics course. If you are interested, you can check it out on my YouTube channel. Otherwise, please remind yourself what is permutation, what is combination. And we even need them for calculating probabilities. So there are also some exercises regarding that, which I already solved in my videos. So this one is necessary for our binomial distribution. You can also show it like this, with this notation, R out of N combination. And this is the formula that you can use in order to calculate it. So N factorial, N minus R, the whole parenthesis factorial, R factorial. And R factorial here, as you can see, is the main difference between combination and permutation. And we use that because we want to decrease the value that you will find here, because order doesn't matter. The number of counting should be less than permutation. Okay, so for binomial distribution, the number of successes in n Bernoulli trials. Okay, so that's why we needed to know about Bernoulli trials. Again, here, the trials are independent, which we should know. And for binomial distribution, we usually denote it like this, binomial. And here, sometimes they show n first, then p. It doesn't matter. But let's say probability of success and the number of trials. Okay, these are our parameters. Like for the uniform distribution, we had A and B as our parameters. Now here we should have probability of success and the number of trials. And in some books, they even show lowercase b for binomial distribution, and they show it like this. Okay, how to find, to calculate it? For example, in binomial distribution, I say what's the probability of x equal to any number, like say, for example, 1. Then in that case, this x that we are mentioning here, the lowercase, corresponds to the question that we are asking you. What's the probability of x equal to 1? Then if you have information about the parameters of the binomial distribution, the only thing left to do is just assign the values for n and p. And what is q? Q is 1 minus p. Okay, so you can always calculate it easily by q is equal to 1 minus p. And x is related to the question that we are asking you. So what's the probability of x equal to 1? You say, okay, x here inside this formula is equal to 1. And the good thing also about binomial distribution is that easily you can find the expected value of x and variance of x by using these formulas. And as you can see, again, we should have the information related to parameters in order to find them. So you should have n and p in order to be able to calculate them. So we should practice with binomial distribution for sure, so that you guys will be ready to also answer questions in the exam. So for sure, in the tutorial, we will deal with binomial distribution. I already told you how to calculate it using formula. There is also another way. Fortunately, for famous distributions like binomial distributions, there are tables related to them so that you don't even need to use a formula. So if you want to use table, you should be careful. These tables are in format of cumulative. What does it mean? It means that you can only answer questions like x less than equal some value from these tables. We should be very careful about this thing that I just told you, because in the formula, you can see there is a equality here, not less than equal. But here in the table, as you can see, we should consider the cumulative version, which is x less than or equal some value. Of course, there are ways in order to convert them to each other. Like say, I'm interested to find this answer from the table, but everything is in the format of cumulative. So what can I do? Here I can consider x less than equal 1 minus x less than equal 0. It will give you exactly the same answer for x equal to 1. But why is that? Let me show you here in this box. Like this is a binomial distribution. Like any discrete distribution, we have pointwise probabilities. So 0, 1, 2, and y corresponds to probability. And these are our x's. So if 0 has a specific probability, we don't know what is it exactly, I can just show it by a point. You don't necessarily need to show it with a line and connect it like the uniform distribution that I showed. Even for uniform distribution, that's not necessary, but you can just show it by a point, okay? And here for 1, let's say this is the probability, okay. So if I'm interested only to find the value of this one, I don't know what's the value of this one. I can calculate it using the formula, or I can use the table. Now, in order to find this one, tables only have cumulative. It means that it has 1 and 0 together. So I have the information of this one. I have the information of this one. What to do? I can calculate the whole thing and subtract it from x less than equals 0. So 0, 1, 2. I have information about this. I have information, cumulative version about this. So the only thing left to do is consider this one and subtract it from the previous one. So what will left is this part, if I do that. So 0 won't be included, and this one will be included. And this gap doesn't have any information because we are talking about integers, so it's the probability is 0, and the only thing left for us is x equal to 1. Okay, so by using this trick you can find it, and we should practice together. So for sure in the tutorial I would try to solve all of them using both formula and table. You should know both of them, so we will go through them in details. And let's say by using the table, the easy question, like just practice with one easy example. Probability of x less than equal 1. Okay, I'm interested to find this one. And I should know what's the distribution. The distribution is binomial, and P is equal to 40%, and N is equal to 6. So I should have information about the parameters. So as you can see in this table, the parameters are given to us. So on this table, N is equal to 6, and P is equal to 40%. So from here, I understand I'm talking about this one, okay? So if you have such a table from P and N, you understood you are talking about this part. Okay, now I'm asking what's the probability of x less than equal to 1? So x's are here. You see? So for 1, I have this probability, and this is the final answer. That's easy. So 0.1866. This is the answer. So you don't need to calculate them if you have the table. So the tricky part is that when they ask you about the pointwise version, but if you practice like this, it will be easy. I will show you in the tutorial how we can calculate them very easily from the tables, and also by calculation sometimes. Another famous discrete distribution is named geometric one. So in geometric distribution, again, we are dealing with Bernoulli trials. That's why Bernoulli trials are very important for us in our such distributions. And what we are doing here, we are trying our trials as much as finally we reach our target. Like I throw a die maybe 100 times in the hope that to reach my target. Or sometimes I don't even know how many times. And in the geometric one, this is also a tricky question. Like how many times should I have this trial to reach it? We can also ask such questions. So, but the goal is that to finally reach success. And when it happens, you stop your trials. Like you throw a die until you reach 2. When you get 2 and that's enough for you, then again, you don't need to try. Like, for example, you throw a die, it happened to be 1. You throw a die, 6. You throw a die, 3. You throw a die, again 3. You throw a die, 2. And it was your goal. So after 5 times, you reached your value that you were looking for. So by considering success as P, you don't have any power for P because it happens only once. As soon as you reach this one, you don't continue your trials. And that's why for Q, the power of that is x minus 1. and 1 is from here. The complement of this one is shown here. Okay, so expected value of x here in terms of geometric distribution, it is 1 over p, and q over p square is the variance. So as you can see, as soon as you notice which distribution you are dealing with, it's very easy to find expected value and variance, and you don't need to go through all those calculations we did in the previous session. But if the distribution is not famous, there's no table for that, so you should calculate everything. So there's another famous one corresponding to Bernoulli Trials, and we call it negative binomial. So in that case, this is a generalized format of the previous one, the geometric distribution. So in this one, the number of successes is not just necessarily 1. So in the previous example, I told you, you continue your trials until you get your target. Assume that I ask you, I need 5 times 2 to be appeared in order for me to consider it my target. So again, I should continue this one until I reach 5 times 2. When it happens, then I need to define it in another format, in another distribution, because geometric distribution only cover until 1 success. If I need k times of those successes, so in that case, we can define it as negative binomial distribution. So you can see here is the formula. K corresponds in how many you want that to happen. So for example, number of 2s, I want to be 5 times, so K should be 5. So as far as you know how to deal with it only once, then they are very easy because you just assign values to them and you can calculate everything. So in terms of probability, you can find using this, and in terms of expected value, you can use these two. Okay, this distribution is very important for us, and also we should distinguish it with binomial distribution. Poisson distribution also has some similarities, which I will explain after this. So in Poisson distribution, we consider the parameter alpha. So alpha is our parameter, which is important for us. In some books also, they show it with lambda. So it depends on you which one you like to use. And as you can see, the interesting part about Poisson distribution is that the mean and variance of this distribution is always equal to the same value. So here, for finding the probability, you can use this formula. E power minus alpha multiply alpha power x divided by x factorial. And E here is just irrational number, right? Irrational number, you can even show it by 2.7 to approximate it, okay? So E minus alpha power x, x factorial. This is the formula that we can use starting from 0 going to infinity. For binomial distribution, we have upper limit for that because x cannot be more than n. What was n? The number of trials. But for Poisson distribution, it can go to infinity, and that's one of the big differences between these two distributions. So as you can see, for parameter only we have alpha. For binomial distribution, we had the probability of success and number of trials, okay? So we should be careful about that. And as you can see in the pictures, again, this is a discrete distribution. So obviously there are gaps between them. So the probability between the gaps are 0, obviously. So only these points matters. Like this point, for example, corresponds to which probability, okay? So you can calculate them easily by using the formula. And for cumulative version, as you can see, all the time starting from 0 going to 1. Because the probability cannot be bigger than 1 and not less than 0. Okay, so this slide also important because we want to know how to approximate binomial distribution using Poisson distribution. In the statistics, we tend to do this a lot, not just for these two distributions, but for other distributions. It's very helpful because sometimes it's not easy to use a specific distribution, maybe because the calculations would be hard, or sometimes the information related to parameters are not given. And in details, I will talk about them, especially when we talk normal distribution, because we will use approximations a lot. But how about Poisson and binomial and how they are related? So in case when the number of trials are large enough, and it depends how you define large enough, like 30 is big enough or not, like 100 is big enough or not, and also we will talk about it in details later. But generally, the concept is that if n is large enough and the probability is small enough. So again, this depends that in which probability you consider less. In some books, maybe 1%, and based on the topic, it could be different on your research. Sometimes the topic doesn't matter which book you are studying. Again, based on the topic, even 1% is not small enough. But generally, when you can decide that what is small, what is large, then based on that, whenever number of trials are big enough and the probability of success is small enough, then in that case, you can approximate the parameter of Poisson distribution by using this formula. So alpha or lambda doesn't matter, okay? So you can approximate it by multiplication of n and p, and easily you can calculate the parameter of Poisson distribution. So with this also we need practice, and we will deal with it in the third tutorial. I hope this lecture was useful for you, but of course we need practice. If you have confusion about these distributions, this is natural, because right after this lecture, please go through the third tutorial. We will practice questions related to binomial, Poisson, and also how to approximate binomial distribution using Poisson distribution. See you guys.